welcome to this video. In this video I am going to explain this problem using SmithChart. So without much delay, so let us see what is this problem is saying. So first is there is a 100 plus j 50 ohm load is connected, so that is our ZL is given, and a 75 ohm lossless line. So here Z0 is given and the line is to be given as lossless. We have to find the reflection coefficient, SWR, load admittance, Zin at this distance, and the locations of Vmax and Vmin, that is maximum voltage and minimum voltage, with respect if the load if the transmission line length is 0.6 lambda, and Zin at the generator if considering this is the length of the transmission line. So we will be doing with the help of SmithChart. Okay, with the help of SmithChart we will be doing. And now before doing what we need, so we need the normalized impedance value. So we have to find that normalized load impedance value, that is equals to ZL divided by Z0. So that is equals to 100 plus J150 divided by 75. So this is the normalized impedance value, we need to find it out. So this value if I calculate, so this value will come as I need to calculate. Okay, so I'll calculate. So after calculating, this value comes as 1.33 plus J2. Okay, so we got the normalized impedance value as 1.33 plus J2, and we need to locate this point in the SmithChart. So how to locate that? First let us see where is the 1.33 line. So here 1.2 is there, 1.4 is here. So 1.33 will some around come here inside that, or else here. This is the 1.33 in real part, and the imaginary part is your one second. So imaginary part is the 2, right? So you see here the imaginary part is 2. So we need to locate the point where 2 is there. So value 2 is here, this one. Okay, I will make it red. So this one is the value 2. So wherever this line and this line, this 1.33 line meets, so that is my required. So how, where it will meet? It will meet around here. Okay, after that you need to draw a straight line passing through that. Yeah, okay. So now this point is what? This point is my load point, or that is my ZL point. So the first question is to find the reflection coefficient. So reflection coefficient, how do we find that? So your magnitude of reflection coefficient is equals to OP by OQ. So where is the point? So this is point O, this is point P, and this is your point Q. Now how do we find that? So we'll measure this length. So you can measure the length with the scale. So this is coming around, just adjust it a bit. Yeah, so now this is coming as around 4.3 or in between 4.4. okay, let me take 4.4 here. So 4.4 divided by this one is 6.7. so that is also we have got in the previous problem, you can refer that. So this value will come around 0.66 or 65, whatever you can. So let us take 66. okay, so if you calculate, it will come in a decimal value, so you can take the next nearest possible value. Now what is the angle of this? So angle you can see, so this is the angle of reflection coefficient, this scale, and this scale here it is 40 degrees. So angle here clearly is 40 degree. So this is the answer to the first one. So reflection coefficient is how much? Reflection coefficient is 0.66 with angle of 40 degree. Next is to find the VSWR. So how to find the VSWR from SmithChart? So to find the VSWR, you need to use this rounder. Keep one point at the center of the SmithChart, that is 1.0 point, and another point at here at the point that we have taken for ZL, and just draw a circle. So let me choose a different color. Yeah, okay. So now we have to draw a circle here. So how do we do? Just through the rounder, just draw this circle. Now wherever this circle is crossing this middle line, so this line is your VSWR or SWR point. So here it is crossing here, 4 is here, 5 is here. So it is exactly not going through 5. So I can take this point as 4.9. Okay. Now what is the SWR value? So your SWR value or S, so that is equals to 4.9 you can take. Okay. So second question is SWR value is 4.9. Next question is to find the load admittance. So how do we find the load admittance? It is very easy in the Smith chart. So what you need to do is just have to draw one more line, and that will give you the load. Which line? So from this point means you have to extend this line exactly in the opposite direction. Okay. So once you extend this line in the opposite direction, so wherever it meets this constant SWR circle, so this point is my load admittance. Now what is the value of this load admittance? We need to find out that as well. So here if you see, so this is 2 circle for 0.2 in the real part, and this is crossing just near to that, so I can take this as 0.22. Okay. So this point will be 0. I'll write 0.22, and the imaginary line you can see 0.3 is here, 0.4 is here. So this imaginary line is coming 0.36 around. So minus 0.36 you have to take. Why it is minus? Because it is in the lower side. So remember, whenever lower side is there, it is taken as negative value. Whenever upper side of the Smith chart is there, it is taken as positive value. That you have to remember. Now this is the YL value. Okay. So what is the YL now? So YL is equals to 0.22 minus J 0.35. Okay. Now this is the normalized Y value. So what will be the actual Y value? YL. So that is equals to small YL means normalized YL into the characteristics admittance. So why Y0 has to be multiplied? Because Z0 is the normalized impedance, Z0 characteristics impedance, and your YL is equals to 1 by Z0. Okay, so finally we can find YL, that is equals to 0.22 minus J 0.35 into 1 by Z0. Why 1 by Z0? Because of this relation between admittance and your impedance. So this Z0 is how much? It is given as 75. So this value will come around if you calculate. So let me just calculate this value. Yeah, the value comes around 3.04 minus, so here minus is there. Next value is 4.67. okay, so this is millicents, so we have to write the unit as well. Now the admittance value is this much, so this is the answer to the second one. Next one is saying Z in at 0.4 lambda. Okay, so to find the Z in at 0.4 lambda, we need to, what we need to do, from the load point, that is from here, we need to travel a distance of 0.4 lambda. So it is saying that if the transmission line is here and ZL is here, so it is asking somewhere distance of 0.4 lambda from the load, what is the impedance value here at this position, somewhere at a distance of 0.4 lambda. So how do we do that? We have to travel a distance of 0.4. 0.4 from where? From the load 0.4 lambda. Now 0.4 lambda is difficult to calculate, so you can take this scale also. So upper scale is there, but I use generally the angle form. So 0.4 lambda is equals to 0.4 into 720 degree, because lambda is 720 degree. So that's how the lambda value is. And if I calculate that, this calculation is coming as 288 degrees. Yeah, okay. So now this 288 degree we need to travel from this load point 288 degree. If I rotate, then I will reach at a point which will give me this impedance after 0.4 lambda distance. Now how do I do that? So see, it is easy. So here it is 40 degree. Okay, now from here to here it is 180 degree. So you don't need to write while you are doing this. This is for explaining. So 180 plus 40, so how much total? 220 degree. 220 degree covered. Now if I subtract this, it is coming 68 degrees. So we have to move 68 degrees more to reach the 0.4 lambda distance. So how do I travel that 68 degrees? Okay, now here this is the point where 220 degree we have reached. Now from here we have to travel a distance of 68 degrees. So 10, 20, 30, 40, 50, 60. So 68 should come around here somewhere. Okay, now next what you need to do? So from the center again you draw one line to the point. So from the center draw one line to this point. Okay, so let us give O, P, Q, R. Let's say this point is R. Okay, now this is the point which represents this ZL or Z in at 0.4 lambda from the load. Okay, so we need to find what is the value of the real part and the imaginary part on this line. So what is that value? So you can see here it is just crossing almost 0.3, right? So it is crossing the 0.3. So real part is 0.3, imaginary part is 0.6 here. Okay, so you can see 0.6 is here, 0.7 is there. So if it is here means, so it is around 0.65 or 66, let us say 66 or 67, you can say plus 0.67. okay, it will be plus because it is coming in the upper side. Now what will be the Z in value? So this is the normalized value, so we'll go here. Now the Z in value is equals to how much? So this is the normalized value 0.3 plus 0.67. okay, so 0.3 plus 0.67 we are getting, and actual value will be into Z naught, that is 75. okay, so this value let me just calculate it. .67 into your 75, so it is around coming 50. So this is equals to 22.5 plus J, it is coming around 49.9, you can take 50 as well. So this is the value at 0.4 lambda distance from the load. So next it is asking that what is the value of what is the location of Vmax and Vminimum point with respect to the load if the load line length is 0.6 lambda. So now let us see here what it is asking. So it is saying that the total length of the transmission line is given as 0.6 lambda. okay, and it is asking from the load what is the location of the maximum voltage and the minimum voltage. So before doing that, we need to know what is the maximum and minimum location will come. okay, so in this Smith chart, so always this side or from the center to the left side, the minimum voltage point is there, V minimum point is there, and on the opposite side, so this side it gives me the V maximum point, and this is on the center line. So that is because some concept of short circuit and open circuit. So while I'll explain the Smith chart in detail, we'll explain that in that time. Now I know the this S-tabular circle represents our transmission line. So this V minimum point will be here. So this is the V minimum point. okay, and this point is the V max point. So now we need to know what is the distance of this Vmax point on the transmission line from the load. okay, before that we need to know that 0.6 lambda means how much degree of rotation. So for that what we need to do, first of all 0.6 lambda that is equals to 0.6 into 720, so that is equals to 432 degrees, right? Now what does this 432 degree means? The total rotation is 360 degree only. So why it is 432? That means it is, we can break that into 360 degree plus again 70 degree. Okay, so that is also can be written as one revolution, means one complete revolution plus 72 degrees. So this is the total length of the transmission line, and we need to find within the transmission line where is the voltage max and voltage minimum points are located. So how do we find that? So for that, first of all, we'll start moving from here and we'll find the distance where is the Vmin and Vmax is coming, right? So first we'll start from here, and when we rotate up to here, we'll get our first V maximum point. Okay, so what is this point? The length of this point is 40 degree from the load. So once it is 40 degree from the load, that means in terms of lambda it is how much? Okay, so your 720 degree is lambda. So 40 degree is how much lambda? That is equals to lambda by 720 into 40, right? So this value will come around, I'll calculate here. Yeah, so this is coming 0.055 lambda. That means from a length of 0.055 lambda we'll get our first Vmax. Okay, let me just wipe this and do it again so that it will be clearly understandable. So what I am saying, this is the transmission line and this is the load. So after traveling a distance of 0.055 lambda, so we'll get a point where the voltage is maximum. Okay, now after this we'll move further because the line length is 0.6 lambda, so we have a more place to go. So here we will again rotate, and here we will get the V minimum point. So what is this V minimum point? So we have to travel some more distance here and we will get a point which is V minimum. Okay, now V minimum, what is the distance of this point from the load? So see here, this distance is how much? We got it 0.055 lambda. And what is distance from here to here? So as it is 180 degree, so I can directly write this. So this is the distance of lambda by 4. Okay, so this is lambda by 4. How? Because total length is lambda, so this is lambda by 4 I can take. Sorry, it got muted. Now this distance is we can find lambda by 4 plus how much? 0.055. So this distance, after this distance, so it is lambda by 4 plus 0.055 lambda. No, not like that. So here 0.055 lambda plus lambda by 4 will give you the V minimum. Okay, now you see, according to our length, so we should have a complete revolution. We have to complete plus 72 degrees. So how much degree we have already completed? So 180 degree plus 40 degree, so 220 degrees completed. Now if I travel further in this direction and again one more 180 degree I can complete. So how? Because from 432 we have traveled a distance of 220, so how many is pending? 72 degrees pending. So I can reach here, I can reach here at this point. So that means traveling from here to here I will cover 360 degree, and after this more 72 degrees still remaining. So from here I need to travel a distance of 72 degrees to complete the full transmission line. Now I know this point is my 40 degree. Okay, so 40, so 30, that means 10, 20, 30, up to 0 it is 40. So then 50, 60, so up to 20, no, so this is 40, up to here it is 60, it is 70, and here it is 72, right. Now this point is 72, that means to with completing 0.6 lambda of distance, so completing 0.6 lambda of distance, I have two V minimum point, right. So first V minimum point is at 0.055 lambda. Second V minimum point will come how much? If you travel here one complete rotation we are doing, that means we are traveling a distance of lambda by 2. So second V minimum point will come. So second V minimum will come at what? 0.055 plus lambda by 2, that is 0.5, so it is 0.55, okay. So 0.55 lambda, that means further if we travel a distance of, means it's a total, not total, distance of 0.55 lambda, then we will get the next V minimum. So first V minimum and second V minimum, we have two voltage minimum points here. And what is the this value? So this value will be around 0.305, right. So we'll write the answer. Yeah, so the answer here is, so location of Vmax, so we have two Vmax. So first Vmax we got at 0.055 lambda, right. Then we got the first V minimum, okay. So V minimum we got at 0.305 lambda, and then the second Vmax will get at 0.555 lambda, okay. So these are the distance from which we will get the Vmax and V minimum. Next is find the Z in at the generator. So Z in at the generator means what? So here you see the total ZL is here, total length is 0.6 lambda, so after 0.55 also some, so this is the second Vmax point. After this still some point is there, and it is asking that at the starting point what is the Z in value. So what to do that? So in the here in this Smith chart we have already traveled a distance of how much? 432 degree we have already covered, that corresponds to how much? 0.6 lambda, that means we are now at this point. So it is asking at once you travel a distance of 0.6 lambda on the transmission line, then what is the Z in value? So for that I need to draw one more line here passing through this, and wherever it crosses the constant VSWR circle, so this point is my Z in point, okay. Now let us see that with this point what is the value we are getting. So it is crossing the resistance circle. I need to remove this first. So it is crossing the resistance circle here. So this one, if I say it is just more than 1, so around near to 2, so it will be around 1.8 or 1.7 also. So your Z in is equals to, so let me just, yeah, so Z in equals to 1.7, and as it is coming in the downside of the Smith chart or the lower half of the Smith chart, so second imaginary part will be negative, and this negative value is coming as how much? So here it is 2, if this is 2, this will come around 2.2. Sorry, my sound was muted. So J 2.2, Okay, now this is the normalized impedance value. So here the question number F answer. So Zin is equals to, so Zin that we got into the characteristic impedance, so that is equals to how much we got? We got 1.7, sorry 1.7 minus J 2.2 into 75. So that will come around, if I calculate, 134, around that. I am not giving a exact value. So minus J 165 ohms, right? So this is the answer that we will get for the Zin. So how do we find that? We have to move a distance of 0.6 lambda from the load, then we will get what is the value of Zin. So like this you can solve using the Smith chart. Okay, so I hope it is understandable, and you can comment me comment if you have any doubt somewhere at any point. I'll try to explain that again. If I can, I will just answer that in the comment, or else if I can't, then I'll try to make another video and explain that. So thank you, and see the next video for the next problem. Have a good day.